Hey, grade 12s. So, in lieu of me actually being told what the heck I'm supposed to do while you guys are away for the next 2 weeks, I decided to make it up as I go along. Um, so, the first thing I've done is a lot of you probably use Discord anyway, so I've created a Discord channel. The link to it is in the email I sent you. Um, I've set up voice chat channels for the for the grade 12s and my grade 9 class, and a general chat as well, which is nice because you can basically put up videos, pictures, whatever, we can communicate. Um, I'm going to ask you guys, give it a thought, email me when is convenient for you guys, and I'll try to set up some office hours where I'll definitely be online. So the entire unit is up now. The only difference you're going to notice for the dynamics and momentum unit is there's this, which is the login for gizmos. I don't know if you've ever used them before. Basically, they're online labs. So each of you has your own login and password, and there's a link to the website with the apps there. So for the ones that use labs, you'll notice there's a gizmo, there's an exploration sheet. Load that up, load up the gizmo, work your way through it. When you're done, just share that with me. That'll be how you do it. It's kind of the way we're going to have to do labs for the near future. So today we're starting with net force and vectors. First thing you're going to notice, oops, got to get back to the first slide, is that the big difference is going to be that, well, there are more than one-dimensional vectors. You're going to actually deal with things that are, on angles. The normal force isn't always going to be the force of gravity anymore. So because net force is a vector, because forces are vectors, the net force is also going to be a vector. You're going to have to add the vectors to actually figure out what the net force is. So when you create your free body diagram, you're going to notice you have vectors, but this isn't actually the vector diagram. You can't get any information from that. To actually find the vectors, you need to add the force of gravity, the force of friction, the normal force, and that'll tell you what the net force on the dog is. You'll notice it actually will make sense if you do it right. The dog should be sliding down the slide because that's what happens on slides. I really recommend using components, looking at vector components when you're doing this, because it can eliminate a lot of work and make things a little more easy to understand. For example, if you look at this question where you've got a 40-kilogram mass being pulled by a person with a rope at an angle, and I tell you, well, what force do you need to pull on the rope with? It's pretty complex because there's a lot of vectors, a lot of things to look at. But logically, you only need, if you're sliding along the ground, to look at the vectors that are in that horizontal plane. So in this case, the force of friction and the horizontal component of the force you're applying to the rope. Because the vertical components, there's one, you're pulling up on the rope, there's a normal force, there's a force of gravity, they all have to cancel out because the box logically stays on the ground. So we only need to look at these two. So you want to find the net force. If it's at a constant velocity, remember, the net force has to be 0. That was the trick from grade 11. Fx, what's the x component of the force you're pulling? Well, it's the force you're pulling with, the tension force, times the cosine of the angle you're pulling, 25 degrees. And then the force of friction is 45 newtons backwards. So 0 equals Ft cos 25. The friction will basically be minus 45 forward, so we have everything in the same direction. So we actually can add these two vectors. So bring that across. 45 newtons forward is F, the tension force, times cos 25. Cos isn't a special number, it's just a decimal, so you can divide it. So the tension force is 45 newtons forward divided by the cosine of 25, which is 50 newtons forward. A lot simpler than it looks like initially. We can also make it simpler. So if you've got a really weird question like the dog on a ramp, you can add the vectors directly or break them down into components. But sometimes you'll notice, like the dog on a ramp, you've got a lot of components to break down. Keep in mind, there's no such thing as a better frame of reference. All frames are equivalent. So instead of looking at it from the point of view of someone standing on the ground, why don't you look at it from the dog's point of view? So the dog's point of view, the dog is on a flat surface. It has a normal force acting straight up on it. It has a force of friction acting along the surface. The only thing on an angle is the force of gravity, which is what's pulling the dog down. So if we rotate it so that the dog's, from its point of view, it's level, now it becomes a lot easier to add the vectors because you only have one you need to break down, and it becomes really obvious, why is the dog sliding in that direction? Well, because that's where the net force is. So the most common example you're going to see of this is a skier. So step one, draw the free body diagram. We're going to forget friction until the next lesson. So this, again, looks kind of complex. You've got a normal force up, because remember, normal force is always normal to the surface. Force of gravity, or the weight, straight down. You don't really see why is the person going up or down the hill. But if you rotate it and look at it from the skier's point of view, now you notice the normal force is straight up like it always is. The force of gravity, the weight, is on an angle. It's pulling you forward down the hill. Now, here's the cool thing. Since you rotated it by 20 degrees to make the hill level, the force of gravity was initially vertical. It's also rotated by 20 degrees. So now it's easy to find the vertical and horizontal components. So let's do it. So the force of gravity is just same as it always is, mass times 9.81. So the force of gravity on the skier is 785 newtons. Now, the y component now will be the component in our down direction. So it'll be the adjacent, so it's the force of gravity times the cosine of theta, so 738 newtons down. The x component is opposite, so it's sine theta, 785 sine 20, 268 newtons forward. Now you can look at it and say, well, wait a minute. Now I know what the normal force must be because it must balance that y component. I know what the x component is because it's the part that's there. So these two are going to cancel out. All that I'm left with is my horizontal component, and that's the net force on the skier forward down the hill. If we added another force, this is what a typical question would look like, and then we'd maybe ask you to find acceleration. Here's the skier, you draw all the forces. Again, you've got two forces you'd have to break down into components. If you look at it from the skier's point of view, the ground is normal force is straight up, air resistance would be straight back. The only force that you'd actually have to break down is, again, your force of gravity, which would have a vertical and a horizontal. Now, important safety tip. If I'm only asking you what their acceleration is, and you know they're not sinking or raising, don't bother with the vertical components at all. You can logically say, the skier is not flying into the air or sinking into the snow, so I can ignore all the vertical components. And we'll just look at the horizontal. Again, there's only two components. There's the x component of the force of gravity pulling you down the hill, and there's the air resistance trying to stop you. So the x component is the force of gravity, which is just mg, times its opposite, the angle, so sine 30, and then minus the force of air resistance forward. Remember, you've got to change the direction. You can't add a forward and a backward. You can only add vectors if they're in the same direction. So we make the air resistance negative, plug in the numbers, you get a value of 400 newtons forward, plug that into F equals ma, F net divided by m, you find the skier sliding 4.7 meters per second squared forward, with forward being down the hill. And that's basically what it is. So, rule of thumb, draw your free body diagram, figure out what the easiest configuration is that you can break down the fewest number of vectors, look for which vectors you want, add them together, and you get an answer. All right, hope that helps.